All right. This may feel a little disjointed. When I first recorded this, my microphone wasn't working. So, what I'm going to do is now narrate on top of my previously recorded writing. So, I apologize if it's a little janky, but that's the way it's going to do. I figure it's better than rewriting the whole thing and re recording the whole thing. Um, so, I'm going to start this and then I will voice over top of it. Um, So one of the things we can get out of an NMR spectrum has to do with the way protons near each other in a molecule interact. Um, and so let's imagine, knowing what you know now, you wanted to come up with what the spectrum for bromoethane would look like. Um, First of all, you'd identify where all the hydrogens are. So I'm going to color code my hydrogens. I've got two sets of hydrogens, the CH3 group and then the CH2 group. And then you want to think about where they would fall in terms of chemical shift. Um, the blue ones are on the same carbon as the bromine. That should shift them from our baseline, which is about 1, up to somewhere around 3, 3.5, because of that electronegative atom having a deshielding effect. So I would expect the blue ones to show up somewhere around 3.5. The pink ones are going to show up around the baseline because they're not really close to the electronegative atom. So if I think in terms of chemical shift and then integral, these pink ones over here are going to fall somewhere around 1, maybe a little shifted to the left, 1.5, because of the bromine nearby. That's going to have an integral of 3. And then the two hydrogens on the same carbon as bromine should show up somewhere around 3, 3.5. And that should be a shorter peak. It should have an integral of 2 hydrogens compared to 3 for the other peak. So that's what you would expect. Now, if you actually go and run this spectrum, you're going to see something much different. So what you see, instead of single peaks for each of these signals, what you see is going to be a and here I'm just labeling A and B. I apologize from the beginning. I should have relied only on color because not everyone's going to see those. But for A, I see, okay, chemical shift shows up between 3 and 3.5, which makes sense. But instead of being a single signal, it's split up into 4 different signals, into 4 different peaks. And then the B hydrogens, they are showing up around 1.5, which is what I expected, but they are showing up as 3 separate peaks. So the question we have to ask ourselves is, why is this? And how can we use this extra information to decode our molecule? All right. So in terms of the explanation, we're going to have to go back to our original explanation of what we originally said contributed to the chemical shift of a given proton. We initially said that there were 2 factors. There was the strength of the magnetic field caused by the machine, and I'm scrolling back to show that, which we called B applied. And we said then there was the induced magnetic field caused by the nearby electrons, because the nearby electrons shield the nucleus from that from that externally applied magnetic field. And then I said there was one other factor. So it's time to talk about that one other factor. So we've got our observed magnetic field, which is going to cause our chemical shift. Now we're saying it's caused by 3 different things: the applied magnetic field, the shielding the B induced uh, caused by the nearby electrons, and then the one other factor. So what is that one other factor? Uh, that one other factor is going to be the neighboring protons. So the nearby protons, oh, sorry, I'm just writing out uh, again where the induced magnetic field comes from. Nearby electrons, uh, they have that shielding effect. And then there's the applied magnetic field, which comes from the machine. All right, so let's talk now about the third factor. The third factor is going to be the neighboring protons. Our neighboring protons behave like little magnets. So they create their own tiny magnetic field. And that tiny magnetic field is going to affect where a given signal shows up. All right. So the neighboring protons, I'll talk in a minute about how we define neighboring protons, but it's going to be the other protons nearby in the molecule, usually 2 to 4 bonds away. Each of those nearby nuclei is actually behaving like a magnet, and it's either going to be aligned with the applied magnetic field or it's going to be aligned against the magnetic field. So we have two different situations for each neighbor. They could be with the field, so they could be enhancing the field, or they could be against the field. So B induced, we said, was a negative factor generally. B neighbor could be a positive factor or it could be a negative factor. So B induced is opposing the applied, so that's why it is a negative factor. The neighbors sometimes are going to be opposing and sometimes are going to be enhancing the magnetic field. For some neighbors, it'll be positive. For some neighbors, it'll be negative. And it turns out about half the neighbors will oppose, and about half the neighbors will enhance. So this factor is going to be kind of a plus or minus factor. Half the time, it's positive, pushing our signal to the right. Half the time, it's negative, pushing our signal to the left. All right. So that's the main idea. All right, continuing on. Let's think about how this applied versus induced versus neighboring magnetic field is going to end up giving us the signal we see. So let's imagine we have just a proton whose signal we're looking at. I'm calling it H observed. And we have a proton we have one proton that is its neighbor. And we want to think about how is that signal going to show up. All right. So I'm going to draw a line here that just represents the initial signal caused by H observed. All right. So this is our expected signal, as if there were no neighbor. So we'd expect a single peak from that one proton. So now if we consider the situation where we have the neighbor, half the time that neighbor is going to have a shielding effect and push it to the left, and half the time it's going to have a de-shielding effect and push it to the right. So my signal is now going to get split 50-50. It'll get half as tall on the left and half as tall on the right. So the arrow the arrow I'm drawing here is showing, okay, if B neighbor has a shielding effect, that's going to push it to the left. Sorry, if B neighbor has a de-shielding effect, it pushes it to the left. If it has a shielding effect, it pushes it to the right. Because because the left side of my spectrum is the more d-shielded side. So I'm going to get these two different situations, and now I'm going to end up with two peaks. All right, those two peaks we're going to call a doublet. It'll be two peaks that are the same height, split by some amount based on that one neighbor. Okay, so one neighbor gives us a doublet. That's the general idea. I'm going to speed this up a little bit. So if I have one neighbor, I get a doublet. What'll happen if I have more than one neighbor? Well, we'll have to consider that situation. Like, how did I end up on that previous spectrum with 3 peaks or 4 peaks, depending on the number of neighbors? That's what we'll look at next. So the idea is when we look at an NMR spectrum, we're going to be able to get information from each signal about not just the chemical environment of that given proton, not just the how many protons are in a given group, but also how many neighbors they have or how many non-equivalent neighbors they have. That's going to be a big deal. I mentioned when I talk about neighbors, generally I'm talking about being 2 to 4 bonds away. Sometimes you'll see 4. That's a little more advanced. So mostly we're looking at 2 to 3 bonds away. So hydrogen bonded to carbon. Sometimes it'll be a hydrogen that's on the same carbon. That'll be pretty rare. Usually it'll be 3 bonds away. So it's hydrogen bonded to carbon, bonded to carbon, bonded to hydrogen. If you have hydrogens on the same carbon, usually they are equivalent to each other. And if they're equivalent to each other, they're generally not going to split each other. We'll look at one situation where hydrogens on the same carbon are not equivalent and they will split each other. But again, most of those situations are more advanced. So you should not really consider that. So generally when two hydrogens are on the same carbon, they're equivalent to each other, so they're not going to split each other. So the splitting really happens from neighbors that are not part of the same equivalent group. All right, so that's the point I wanted to make. So we've considered what happens when you have one neighbor. That is pretty straightforward, but we can see in the previous case, all right, I didn't get just a doublet. I got more. So if I consider my B hydrogens, they have 2 neighbors. And if I consider my, and they ended up with a triplet, so 3 peaks. If I consider my A hydrogens, they had 3 neighbors. And that ended up giving us a quartet. In general, we're going to see that pattern that whatever number of neighbors you have, you're going to end up with one more peak than that. So 3 neighbors yields 4 peaks, 2 neighbors yields 3 peaks, and so on. That's what's known as the N+1 rule. So that N+1 rule is just relating the number of neighbors to the number of peaks that you're going to see. Let's look a little deeper into the origin of that N+1 rule, because it's not obvious that it should be that way. But let's imagine the case where we have 2 neighbors, and then we'll imagine the case where we have 3 neighbors. So if I'm observing one hydrogen, all right, I have my expected peak, then I would consider what happens with the first neighbor. So with the first neighbor, half the time, that's going to split my signal and send half of my signal to the left and half of my signal to the right. So if I consider the effect of the first hydrogen, I'd expect 50% to go to the left a little bit, 50% to go to the right a little bit. I can see why people usually speed this up. All right, so my first neighbor splits me, and I get two new peaks that are half as tall. Now I consider the effect of the second neighbor. So the second neighbor is going to take each of those peaks and split half of them to the left, half of the signal to the right. When I do that, notice two of them will meet back in the middle. So in the middle, I'm going to get a peak that is, this half as tall as my original. But then on the two outsides, I'm going to get two peaks that are a quarter as tall. If we consider another way to think about this, instead of drawing that splitting tree like I just did, is I have two situations, or I have four situations to consider. I have my two protons, and the first one could be aligned with the field, second one could be aligned with the field. First one could be with, second one opposed. First one opposed, second one with, and then both of them opposed. So those are the four situations. And since it's roughly a 50-50 split, each of these situations is going to happen about 25% of the time. So 25% of the time, I will have both of them with the field. 25% of the time, I'll have both of them opposed to the field. And then notice about half the time, I'm going to have two of them, one of them with the field, one of them against the field. In that case, they cancel each other out, and so my peak stays right in the middle where it was. But then I have the other quarter of the time where they're both against the field. So that's why I get these three peaks with a height ratio of 1 to 2 to 1. That's what we call a triplet. So you see the triplet right here on the screen. That is three peaks, 1 to 2 to 1 ratio. That's what we'd expect when we have two neighbors. What if we have three neighbors? Then I'll walk through that one relatively quickly. But now my situation is a little more complicated. But again, I could lay out all the possible situations where they're all aligned with the field, where two of them are aligned with the field, where one of them is aligned with the field, and then where none of them are aligned with the field. All of them are opposed. So I'm laying out all the situations. Now we have 9 different situations. Okay. So now 1/9 of the time, they're all aligned with the field. 1/9 of the time, they're all opposed. So I'll get my two little peaks on the outside. Sorry. Did my math wrong in my head. It's 1/8 of the time and 1/8 of the time. Sorry about that. And then 3/8 of the time, I'm going to have two of them lined with the field and one opposed. And then 3/8 of the time, I'm going to have two of them opposed and one with. All right, so now my peaks should be in a 1 to 3 to 3 ratio. All right, and if I look at my quartet here, I've got a 1 to 3 to 3 to 1 ratio of my peaks. All right, so when we have three neighbors, we'd expect a quartet. We can expand this pattern and keep going and kind of make a chart of what this n+1 rule yields. So if I have no neighbors, I get a singlet. Okay, that's just a single peak. Right now I'm describing what's called Pascal's triangle, which you can do to figure out what the ratios will be. In Pascal's triangle, you keep expanding outward, but each number is the sum of the two numbers above it. So in this case, 1 + 1 = 2, so that middle number is 2. So in a triplet, I get a 1 to 2 to 1 ratio. In the next row for a quartet, I get a 1 to 3 to 3 to 1 ratio. which we just showed. And you can just keep doing that. 1 plus 3 is 4, so 1 to 4 to 6 to 4 to 1, and so on. You can keep going. 1 to 5 to 10 to 10 to 5 to 1. It's kind of a fun little math phenomenon. These actual numbers are not that important. What you really want to notice from this pattern is that you always get peaks that are really small around the outside and get bigger toward the middle. If there's an odd number of peaks, you get one peak that's highest in the middle. If there's an even number of peaks, you get two peaks that are the same height in the middle. And it forms kind of a pyramid structure where they're getting taller until you get to the middle, and that's it. So we have names for all these things. And here I'm just drawing a rough sketch of what each one looks like when it shows up in your NMR. Again, the specific numbers aren't important. The pattern is what's important. So I'm sure when I'm drawing these, I'm not getting the ratios quite right, especially for this one. Those little peaks on the outside are often so small that you can't even see them. But I'm doing my best to try and mimic the actual height pattern in C. So there you go. The n+1 rule yields these different patterns, and so you should look for those. And when you see these, it tells you about how many equivalent neighboring protons. So not equivalent to the one we're observing, but equivalent to each other, how many there are. That can make a huge difference in determining structures. You'll see when we do examples that the splitting patterns often help us rule out certain possibilities for identities of our molecule. Take a minute and pause now, and here are some different groups that you will run into. So I'd like you to pause and then come back and see if your predictions for what the pattern would look like match what the actual outcome is. So make a prediction. Right now, all I'm doing is drawing in the hydrogens on each one. You should pause. You should do that for yourself, and then think about what pattern each of these would yield. And come back when you're ready. All right, I've just taken some time to lay out and label all my hydrogens. Now I'm going to start drawing the patterns. So in this first one, I have HB. Those are 2 protons with 3 neighbors. 3 neighbors, I should expect a quartet. So this is when you have an ethyl group. You'll get 2 hydrogens that show up as a quartet. And then your 3 hydrogens, the ones I've labeled A, those should show up as a, those have 2 neighbors, so those should show up as a triplet. So in this case, I'd get a 2 hydrogen quartet and a 3 hydrogen triplet. Generally, since X is probably more electronegative, the B protons are going to be more deshielded, so they'll show up to the left. And the 3 hydrogen group will show up to the right. All right, the next one is an isopropyl group. When I have an isopropyl group, now I have 6 hydrogens that are all equivalent to each other, and they've got that one neighbor in the middle. So my 6 hydrogens should show up as a doublet. My B should show up as a doublet. But my A should show up as a doublet, but now my B hydrogen has 7 neighbors, so it should 6 neighbors, so it should show up as a septet. So when you see this pattern where you have one hydrogen that's all split up and then a doublet for 6 hydrogens, that's an isopropyl group. If you have a tert-butyl group, it's pretty boring because you have 9 equivalent hydrogens, so they all show up together. These next couple, in this case, when you have a benzene ring with one substituent, technically there are 3 different groups of equivalent hydrogens there. So in theory, we should see 3 different peaks. Occasionally, you will see that. More often, these peaks have similar chemical shifts and they get split, and the splitting patterns can be complicated. So in theory, there is going to be a pattern that would emerge, and maybe if you had a powerful enough machine, it might separate them all. But more often, what you're going to see in this case is just a jumble. So there's, like, in theory, what this might look like. You get 3 signals, each with its own splitting pattern. In practice, what you get is usually just a jumble. But the key here is the chemical shift will be somewhere between 7 and 8. So if you see a jumble between 7 and 8 of 5 hydrogens, you know you have benzene with just one substituent coming off of it. One splitting pattern that is more common and is easier to see is when you have benzene that is what we call para-substituted. So the 2 groups are directly across from each other. When you have that situation, now you have 2 different groups of hydrogens, which I labeled A and B, that are equivalent to each other, and each one has just one neighbor. So this one is going to be much clearer because you'll get 2 doublets, and again, they'll be in that 7 to 8 region of the spectrum. Both of these benzene ring, you're looking in the 7 to 8 chemical shift region. So the only splitting pattern I would expect you to really be able to distinguish would be when you have this para substituted benzene, because you do get a clean 2 doublets splitting pattern. So that's one to watch out for. Again, some of these things might seem sort of esoteric right now. When you start seeing examples, and you'll get plenty of practice, then they will make a lot more sense to you, I promise. All right. Now I want to talk a little bit about some special situations, because these patterns of doublets, triplets, quartets, etc., they assume that the effect of each neighbor is identical. But it turns out that not all neighbors will necessarily split you by the same amount. Generally, the coupling constant is measured in Hertz. The coupling constant essentially is how big a split that neighbor is going to cause. You don't need to remember numbers on this page at all. You also don't really need to worry about the situation where you have geminal hydrogens, so 2 hydrogens on the same carbon that are splitting each other, except for this alkene situation down here. I also mentioned that with these aromatic rings, the splitting patterns can get complicated, partly because hydrogens that are 4 bonds away can split each other. That's something to save for a higher level class, not this class. So the one situation I do want to talk about in this class, because sometimes it's helpful in drawing distinctions between molecules, is the idea when we have an alkene, the neighboring protons will split each other, and essentially we end up with 3 different ranges of splitting constants that I like to call small, medium, and large. So the 2 hydrogens together on the end of an alkene have a small splitting. Sometimes it's so small you can barely see it. If you have 2 hydrogens that are cis to each other on that alkene, they have a medium splitting. And if you have 2 hydrogens that are trans to each other, they have a large splitting. So I'm going to show you what that looks like in practice, because it ends up giving us a more complex splitting pattern. So if we pick one of these hydrogens, even though it has, in theory, 2 neighbors, those 2 neighbors are not going to split each other the same. And therefore, we won't get a simple triplet the way that I described earlier. Instead of a triplet, we're going to get something that's a little more complicated. So here I'm just laying out when I consider A and B splitting each other, they have the small split. A and C splitting each other, they have the large split. And then B and C splitting each other have the medium split. So now I'm going to lay out what that splitting pattern is going to look like for each of those protons. So if I consider A, first, I'm usually going to do the big split first. So first I'm going to do the A to C split. That's going to be large. So I start by splitting that signal with a big wide gap in between. Now I have two peaks with a big gap between them. Then I'm going to do the small split caused by B. And so what do I end up with here is I end up with a doublet and then a gap and then another doublet. So I've got my large split and then my small split. So in practice, what I'm getting here, instead of meeting up in the middle the way they did with a triplet, when I had the splitting constants exactly the same, here with different splitting constants instead of a triplet, I'm getting what we call a doublet of doublets. So I'm getting two separate doublets. And here I'm just describing all of my peaks would be the same height, but it would be sort of two together, gap, two together. That's what the signal for hydrogen A would look like. Now, if I consider hydrogen B, now I'm going to have medium and small. So now I would start with a medium split, and then I would do a small split. And if I do the medium and then the small, again, I get a doublet of doublets, but now there's not as big a gap in the middle. It almost looks like I have four peaks that are fairly evenly spaced out. So again, I get a doublet of doublets, but my peaks are a little more evenly spaced out. If I consider hydrogen C, now that's going to have the large and the medium, and here I'm going to really have my four peaks very evenly spaced out, because I have the large split, I have the medium split. So in this case, from these hydrogens, each one yields a doublet of doublets. So that's four peaks, same height. The way they're split up is going to be a little different. I'm going to kind of draw a reasonable facsimile of that at the bottom. And then when you're doing practice, you'll see at least one, maybe a couple examples of this. So I have my large and medium, so that's hydrogen C. That is on the carbon bonded to the oxygen in this case. So that's going to be more de-shielded, so more to the left. And that those four peaks are evenly spread out. Then I'm going to have hydrogen A that's going to have tiny split, big split, tiny split. Hydrogen B that's going to have tiny split, medium split, tiny split. So those are my different peaks. I don't know why it just got blurry. That is very strange, and I'm not a fan. One thing I'm pointing out now, there it goes, is that there is resonance involved here. So this molecule has an alternate resonance structure. And in that alternate resonance structure, my far carbon that has HA and HB has a negative formal charge. So there's more electron density around them. That means A and B, normally I'd expect on an alkene to show up between 5 and 6. But A and B, because there's extra electron density there because of resonance, that's going to get pushed to the right, more shielded, and end up closer to 4, 4.5. So that's what I'm pointing out there. Again, this is a lot of information, but when you start doing practice, it will make a little more sense. So finally, I'm going to close with a few little tidbits. Number one, when you have heteroatoms like nitrogen and oxygen, those hydrogens can get involved in hydrogen bonding. And because of the way hydrogen bonding works, and those hydrogens can get exchanged from one molecule to another, they generally don't participate in splitting. So they'll always show up as a singlet. And that singlet often is kind of broad. And it's really because the peaks get blurred together because of the way the hydrogens are getting exchanged by um, hydrogen bonding. So those will show up as broad singlets generally. Um, you might also see, because of that, if we put this in a solvent like D2O, so hydrogen, so water with deuterium on it, those NH and OH peaks, because of hydrogen exchange, they can get replaced with deuterium, and they can disappear. So if you ever see exchanges with D2O on a spectrum, that's probably an OH or an NH peak. And then sometimes you'll see splitting patterns that are more complicated, and you can't really tell what is going on with those more complicated splitting patterns. Just be a little flexible with yourself there. The spectrum might not be perfect, so you might have to squint a little. So, for instance, and then the last point on that page is that you will see that we generally can't have a solvent that has hydrogen atoms on it, or at least hydrogen with one proton. So we generally use deuterated solvents that have deuterium instead. Um, and deuterated is just one of my favorite words to say, so I wanted to throw it in there. So the key is hydrogen with a neutron in the nucleus does not have a nuclear spin, so it has no effect on NMR. So now you know all the background that you need to start solving problems with NMR, to start looking at molecules and predicting or looking at spectra, and then predicting what the actual molecule represented is. So in the next part, I will be discussing how I'll be walking through a couple examples. All right, let's dive in and do some practice problems. So the first thing I want you to do is look at this page, think about all the information you see, and start to try and come up with some ideas. All right. Once you've done that, so pause, go ahead, look at all the information you have, think about what you know, and then come back and I'm going to walk through my process. All right. So when I approach this problem, the first thing that I'm going to do is think about what the chemical formula tells me. So you may remember that when you have a chemical formula, one of the first things you can do to start thinking about potential structures is to calculate the number of degrees of unsaturation. So the first thing I would do in any structural identification is calculate the unsaturation number based on the chemical formula. Remember that chemical formula comes from mass spec. I won't ask you to interpret mass spec. You may take a course in the future, though, that does ask you to interpret the mass spec and come up with the chemical formula yourself. If you do, then that'll be your first step. But once you have the chemical formula, calculate that unsaturation number. I get an unsaturation number of 5. As soon as I see the unsaturation number is greater than 4, I start to think that there may be a benzene ring, because that takes care of 4 degrees of unsaturation on its own. So it's not a surefire thing, but I do start to lean towards benzene as a possibility in this case. So lean toward benzene. Great. Then I would dive into my IR, and I'm looking for 4 things usually in my IR. I'm looking for OH, I'm looking for C double bond to O, I'm looking for C double bond to C, and I'm looking for triple bonds. So this one has a C double bond to O peak, so I know I'm going to have a carbonyl in my molecule. It also has a C double bond to C peak at 1600, and it has those benzene overtones, so that's more evidence that likely that C double bond to C is really a benzene ring. So probably I have a benzene ring and I have a carbonyl. That would account for my 5 degrees of unsaturation. 4 for the benzene ring and 1 for the C double bond O. There is no OH peak over on the left, so OH is probably absent from this molecule. And there's also no triple bond peak in that 21 to 2300 range. So there's probably no triple bonds. So I look at my IR, I look for those four things. And great, now I'm going to go to my NMR. And what I might start doing is building a library of pieces that I'm going to have to put together. So I'm already putting in a benzene ring that I think is there. And I'm putting in my carbonyl that I think is there. So my degrees of unsaturation are taken care of. 7 of my carbons are already taken care of. Now I got to come up with the other pieces. So take a look at the NMR spectrum. First thing, I see that that jumble of peaks in that 7 to 8 range. All right, that's more confirmation that I have benzene since there's 5 hydrogens represented. That tells me there's only one substituent on my benzene ring. So that piece has 5 hydrogens. Great. So that's locked in. Now I look at my other peaks. I have a 2 hydrogen peak. The expansion above is showing me more clearly that the one at 3 is a triplet. The one at 1 is a triplet. And then the peak that's at like 1.8 or so, that is really split up. It's a little hard to tell how many peaks it is, but it's a bunch of peaks. So my 2 hydrogen peak tells me that I have a CH2 group with 2 neighbors. So that's going to be another piece that I'm going to try and put together. My 3 hydrogen triplet tells me that there's a CH3 group with 2 neighbors. So I have a CH2 group with 2 neighbors. I have a CH3 group with 2 neighbors. And then I have this peak in the middle that looks like, it's a sextet. So it looks like it has 5 neighbors. So you might start to be able to put this together. All right, I have 2 hydrogens with 2 neighbors, 3 hydrogens with 2 neighbors, and then 2 hydrogens with 5 neighbors. So probably I have a CH3, CH2, CH2, CH3. But I put all those pieces in separately. And now I'll try to assemble my molecule. And I'm going to put those different pieces together in whatever combinations I can come up with, and then compare to the spectrum and see if I can rule any out. So what I do is I assemble them in the ways that I can see are possible. So one way is that way, where I have my carbonyl and then CH2, CH2, CH3. I could have CH2 and then carbonyl and then CH2, CH3. And I could have CH2, CH2, carbonyl, CH3. Those are the only ways that I can possibly assemble the pieces that I have. And now I want to think about which one fits the splitting pattern. Well, the only one that fits the splitting pattern is going to be the one that will show me having 2 hydrogens with 5 neighbors. That peak that's at a chemical shift of about 1.8, 2 hydrogens with 5 neighbors. Only one of these possibilities has 2 hydrogens that have 5 neighbors. Notice this one, I would have a CH3 group with no neighbors, and my CH3 group should have 2 neighbors. Great, so I can rule that one out. My next one is going to have a CH3 group with 2 neighbors. Okay, that part makes sense. But then it has a CH2 group with no neighbors. All right, so that part makes sense. But then I look at my other side. I have 2 hydrogens there with no neighbors. My spectrum doesn't have any singlets, so that is not a possibility. So my only possibility left is the one on the left. I have 2 hydrogens with 2 neighbors. That's the peak at about chemical shift of 3. I have 2 hydrogens with, so I'm just color coding those. I'll call those A, and I'm probably going to go label the peak as A. Great. Then B, is going to be my 2 hydrogens with 5 neighbors. And then C is my CH3 group, which is over there on the right. All right, so using all the information from the spectra, I was able to come up with a solid determination of what my molecule is. That is our goal. Our goal is to be able to isolate a compound in the lab and then characterize it using these spectroscopic techniques. So here's one more practice problem. I'd like you to pause, and then when you're ready, come back and go through the steps with me. But pause. Really try and solve this on your own, and then come back. I'm demonstrating the pause right now. All right. Hopefully you weren't stubborn and didn't pause and didn't go through this. And hopefully you went through this on your own. But if you didn't, well, I can't stop you. So first I decided I found the unsaturation number. Then I looked at my spectrum. I could see, again, there's probably a benzene ring. In this case, there's an OH group. There's no carbonyl. There's no C double bond O. They're at 1700. And there's no triple bonds again. All right, unsaturation number of 4, probably benzene again, and that would take care of all my degrees of unsaturation. So great. I look down at my spectrum. I got a jumble of 5 hydrogens at a chemical shift of 7 point something. That confirms my benzene, and I know I have OH. So I'm building my library of pieces. All right. I've confirmed benzene, and it's only going to have one substituent because it has 5 hydrogens on it. Then I'm going to look at my other peaks. 2 hydrogens, that seems to be a doublet, so that's going to have 1 neighbor. And based on its chemical shift of about 3.5 to 4, probably the oxygen is going to be bonded to that CH2 group. That will give it the chemical shift of about 3.5, which I expect. So I'm using chemical shift there to determine, all right, probably that's going to be where the oxygen is. So I probably have a CH2OH group. Next, I see this peak. It's kind of a multiplet. It's got a bunch of neighbors. This is where I said you got to be flexible, but it's 1 hydrogen with a bunch of neighbors. I'm saying 5 here. Well, first I said 5 because I knew it was 5. You can see there's 2 peaks, similar height in the middle, so I'm guessing it's probably an odd number of neighbors, so I have an even number of peaks, so 5 is a decent guess. Then I have a 1 hydrogen peak. That's a singlet. That is probably going to be my OH peak because remember, hydrogens on oxygen are not going to participate in splitting, so they'll always be singlets. And then my 3 hydrogen peak, well, that's going to be a CH3 group. And it's only got 1 neighbor. All right. So now, in order to assemble these pieces, I've got these pieces. I've just got to put them together. And really, there's only one that can be in the middle. That green one, that carbon with 1 hydrogen, has to be the group in the middle. And then the other 3 just have to branch right off of that. So I can only come up with 1 possibility here, and then I'm going to double check and make sure that it fits everything about my spectrum. So I've got my CH group, and then coming off of that will be my CH2OH group with 2 hydrogens, and then also coming off my CH group is going to be a methyl group. So if I look at this, the chemical shift for the methyl group right around my baseline makes sense. Chemical shift of my 2 hydrogens with bonded to the OH will make sense. My 1 hydrogen peak, since it's got a bunch of neighbors, it's got 5 neighbors, and it's right next to the benzene ring, and not too far from the OH group, that's going to shift it to the left. So its chemical shift of about 3 makes sense. So this molecule matches my spectrum, and I can feel pretty confident that this is what I've isolated. Right there, I'm zooming in to say, oh yeah, it makes sense that that would be 5 neighbors, because it looks like a sextet. And that is essentially your process. So practice it and enjoy it.